Hi, everyone. Today we're going to talk about infrared spectroscopy. So this is a second technique on how to collect data to help us figure out what a molecule looks like. Another part of structure elucidation. Okay, so we're in Key Concepts, Unit 4, Part 2, infrared spectroscopy, or IR. So out of all the instruments, this is my favorite. This is the one that is pretty straightforward. Usually doesn't take much time to analyze and get information out. So hopefully this video won't take too long either. So here's the idea. I wanted to go over a little background material, explain what's going on, and at the end, we'll just go and look at an infrared spectrum and try and figure out what it's telling us. So a little background first. There's also a separate video on the theory of infrared spectrometers, the equipment and how they work. So take a look at that. So right here, we're just going to look at the theory of the data and what we're acquiring and how it tells us something about the molecule. All right, so infrared spectroscopy deals with infrared light. Essentially, you're going to shine infrared light on our molecules. So what's infrared light? Well, it's something that's invisible to our eyes. Infra means kind of inside or below the red light. So I like this, found it on the internet. Great place for info. Here's all the colors that we can see. And turns out that different wavelengths of light correspond to different colors. That's kind of cool. The eyes can actually pick out the energy or the frequency of light and tell our brain, hey, well, this light of a certain frequency is orange and this light of a different frequency is blue. And then once it gets to red, they're longer wavelengths and lower energy, and our eyes don't pick them up. We don't detect them. And that's infrared light. So if you go and measure the wavelengths, you got 400 to 700 nanometers. So we're below that, so greater than 700 nanometers. And here's the range up to 100,000 nanometers. And so now let's get out of nanometers because this number is too big. Nano is a billion. 10 to the minus 9 meters, a billionth of a meter. So let's go to a million, a micron. And then we got those numbers, 0.7 to 100. So those are the wavelengths of infrared light we want to look at. Well, here's the idea. When you talk about energy and light, the equation from physics is energy equals Planck's constant times the frequency, h nu. So wavelengths, one way to look at light, but oftentimes we're going to look at the frequency. So let's switch it around. Maybe that's not the right place. Back up a little bit, Dennis. Hey, so here's the infrared region, 700 to 100,000 nanometers, which is 0.1 to 100 micrometers. And within this range, because that's really wide, we're going to take a subset of wavelengths between 2,500 and 25,000 nanometers, or now let's get out of nanometers, get out of micrometers and go to centimeters. Yeah, okay. So there's a range for centimeters. Weird, I know, it's just unit conversion, different wavelengths. Okay, so shine infrared light on a molecule and what's going to happen? Well, turns out that molecules will absorb infrared light if they have some type of vibrational mode that matches the frequency of that light. So we just said E equals h nu. Nu is the frequency. Oh, here's nu again, different way to draw it. The wavelength times the frequency equals the speed of light. That comes from physics too. Wavelength times frequency equals the speed of any wave, sound wave, wave crests on water, so forth. And all right, so all this paragraph here is just talking about how we're going to measure that wavelength or the frequency. We have a choice. Let's go back up here to the guiding principle. Shine light on a molecule. And sometimes the light just goes through. The molecule appears to be transparent. Other times the molecule will absorb the light. So what's going on there? Well, for infrared light, it turns out that some molecules can absorb certain frequencies or wavelengths, depending on how you want to talk about light. The infrared light gets absorbed by molecules if we have a matching of the frequencies. So it's the idea that the frequency of light can match the frequency of a bond vibration. All right, so here I got a couple of things for you. Switch screen sharing. Let's go over to Wikipedia, I think. I'll look at bond vibrations. So I will make sure that this is showing up. So one more time. So this is kind of cool. So what we have here is, maybe this is a carbon atom. It's making 4 bonds. I see a dash and a wedge down here. 2 more bonds here. Maybe these are hydrogens. Maybe they're halides. I don't know. The bonds. These are atoms, the little circles on chemical bonds. Sort of like springs. And right here, there's 6 ways that a chemical bond can vibrate. You got these, the stretching of the bonds. They can go together symmetrically, or they can go opposite. The bonds can kind of wag back and forth. Well, I guess this one's wagging. This one's scissoring, and this one's rocking, and that one's twisting. Okay, so there's different ways, different modes where bonds can vibrate. Now, this page is a little misleading because all these bonds appear to be vibrating with the same frequencies. And in the real world, molecules, they don't vibrate with the same frequency as you look at the different ways or different modes they vibrate. No, the different vibration modes have different frequencies. So a molecule with one chemical bond can actually absorb at least 6 different frequencies because it can it can vibrate 6 different ways with 6 different frequencies. Okay, so here's different ways chemical bonds can vibrate. They do it at different speeds, different frequencies. And then what's this idea about infrared light matching the frequency? Well, it's sort of like this. Let's look at this bond right here, just going in and out, up and down. And if you come in with a wave that's going, where's my pin drawing? There we go. No, oh, because I'm not, I'm not in paint. Let's go to this one where I can draw. I think this will draw now. Okay, so bring in a light wave that's going in and out. And if I'm matching, I think I'm matching. Okay, so the frequency is matching the frequency of, so this is light. And as I was drawing it, I was trying to match the frequency of this vibration. So rewind the video and see how I did. But if there's a match, then this frequency of light will be absorbed and this bond will vibrate faster, right? Because light carries energy. The energy is proportional to the frequency. And if the bond absorbs that energy, well, then it vibrates faster. This is very much like going out to the playground and swinging on a swing. So let's go to a different one. Sorry, I guess I should have went there. And I don't trust Canvas. Oh, sorry, this is Zoom. So let's make sure I'm sharing it right. I think I am. Okay, so found this little motion picture here, this little animation. And what I want you to look at is, hopefully you had a chance as a kid, or maybe as an adult, to go on a playground and swing on a swing set. And the idea is that you can, if no one's there to push you, then you can pump your legs and get the swing to swing by itself, the rock back and forth. The key is to time it, right? So this kid is sticking out his legs, and he goes up, he tucks them, and he goes back. And if he tucks and extends his legs at a different rate, a different frequency, then he's not going to be able to pump and make the swing go, right? I don't know. As a kid, I remember watching some little kids trying to learn how to pump their legs to make themselves go up and down on a swing like this. And, you know, at the first time they try it, they don't get the hang of it. They just rapidly move their legs back and forth and they go nowhere, right? They put in too much frequency and it doesn't work. You have to match the frequency. So extend and tuck, extend and tuck. And you have to wait till you reach the top before you tuck. And if you do it wrong, you actually don't make yourself go faster. You actually stop the swinging. And that's the idea. You put in energy with the right vibration through the pump of your legs. It's sort of like a wave. And you make the swing go higher. It vibrates more like the chemical bond. Man, hope that helps. That's the whole idea between infrared and spectroscopy. Okay, so more specifics. Okay, so we talked about wavelength and frequency. They're inversely proportional, right? So if you know its frequency, here it is. If you know the frequency, it's inversely proportional to the wavelength. So we talked about measuring infrared light, and this is the region, 0.25 times 10 to the minus 4 centimeters to 2.5 times 10 to the minus 3 centimeters. That's a wavelength. But the light absorption is proportional to the frequency. So the old chemists, when they're designing the instrument, I don't know what their hangup was, but this is what happened. They said, well, what's most important for absorption is that frequency matches. So we're all about the frequency. And then the experimentalists or whoever's designing the equipment said, yeah, but what we have is something to measure the wavelength. And so they compromise. And it's an odd compromise. They said, okay, frequency, which is what we want, is inversely proportional to wavelength, but that's the number we can measure a little more accurately in our instrument. So guess what? We'll measure the wavelength and we'll switch it upside down. We'll take the reciprocal of it. And that is proportional to frequency. All you have to do is multiply this by the speed of light, and then you have the frequency. Why am I talking about all this? Because here is a silly infrared spectrum over here. And you can see there's a unit of 4,000 here, and then it's 3,500. Well, what's the units of 4,000? It's reciprocal centimeters. It's centimeters to the minus 1, or, you know, cm and the denominator. Or you can just call them reciprocal centimeters. Those are the units for infrared spectroscopy. And I'll just get used to it. You don't really have to worry about it, but if you're curious, that's what's going on. One more little nuance about infrared spectrum, about infrared data. So the first thing is we measure in these weird units, reciprocal centimeters. Somehow we got frequency, but we're measuring the wavelength. Wavelength is in meters, but centimeters is more convenient given the numbers. Yeah, whatever. Second weird thing. So the early detectors, they didn't measure how much light was being absorbed. No, they have a detector that it itself absorbs the light. So what you do in your infrared spectrometer is you have a light source that can shine infrared light. Infrared light comes out, you put your molecule in the way, and you change the frequency of the infrared light, and then sometimes the light is absorbed. And sometimes not. If it's not absorbed, the light goes through and hits the detector on the other side. And the detector goes, wow, I'm getting a whole bunch of light here because the organic molecule is not absorbing anything. And then the organic chemist says, yeah, I don't care. I want to know which frequencies are absorbed. So then light comes in at a different frequency, different reciprocal centimeter. And this time the molecule absorbs it, and now very little light gets through. And the detector on the side says, whoa, I'm getting very little light here. Not much is getting transmitted to me. That's how the early machines worked. So over here on the y-axis of our infrared spectrum is percent transmittance. How much light is getting through? If there's no light being absorbed, 100% gets transmitted through. If all the light is being absorbed, then 0% is transmitted through. And that is what we want to know. It's like, hey, at this wavelength, it looks like it's around 3,300. There's a whole bunch of light being absorbed. None of the light, or very little light, is actually getting through the molecule. It's all being absorbed. And at 4,000, it's nearly at 100%. That's boring. No light is being absorbed here. But there's something interesting happening. There's some chemical bonds vibrating faster because light is being absorbed at 3,300. Here, let me show you the whole infrared spectrum. This molecule is the molecule found in beer and wine. It's ethanol, an alcohol. Hey, there's the OH group. Yeah, because it's an alcohol. And we scan this region from 4,000 reciprocal centimeters down to, well, about 400. Here it's got 500, a little less than that. And look at all these absorptions. Well, technically it's transmittance. But right here, a whole bunch of light is being absorbed. Right here, a little bit of light is being absorbed here and here. A whole bunch being absorbed there. A bunch of light absorbed there and here. Anyways, these peaks are upside down. That's goofy. You can find some modern infrared spectra where it's been reversed. They actually plot absorbance on the y-axis, so all these get flipped upside down. But it's a generational thing. All the early chemists were taught how to read this type of spectrum, so they teach their students how to read it. I was taught how to read it this way, and so people keep producing this spectrum where the peaks are upside down. And I'm passing it on to you because this is still the most common form of the infrared spectrum where the peaks are upside down. Okay, that's the weird technical side of the data. Let's get on to the analysis. Like, okay, we got a bunch of light being absorbed at 3,300, more light being absorbed at 3,000, nothing here around 2,200. What does that tell us about the molecule? It actually tells quite a bit. Okay, let's back up a little bit. What else am I missing? Well, there's the punchline. Infrared spectroscopy identifies functional groups. So what's that all about? How can I identify functional groups? Well, let's go back to Wikipedia. Yeah, kid on the swing. You keep having fun. Here we go, vibrational modes. Hope that's working. Double check that it is. Okay, so remember, this is not accurate. When you change the vibrational mode, this rocking versus a stretching, the frequencies will be different. Okay, these are all chemical bonds, right? Covalent bonds. You can think about them like a spring. Okay, if you play with a spring, you know the big, long, loopy ones, they vibrate very slowly, and the tight, really strong type, very thick wires, they vibrate very quickly. They're stronger springs, they vibrate very quickly. They should have brought in some springs, demonstrated, but you got the idea. Chemical bonds work the same way. A very strong bond vibrates very fast, and a very weak bond vibrates more slowly. It stretches more, and it relaxes and stretches and relaxes. So what's a strong bond? A single bond, a double bond, or a triple? Triple bonds are the strongest. There's 3 bonds holding the atoms together. So a chemical bond's like a spring. The tighter the spring, the stronger the spring, the faster it vibrates. So if you look at a carbon-carbon single bond, we're going to get low frequency infrared light absorbing there. Double bond stronger, it's going to vibrate more quickly. So higher frequency infrared light. Triple bond, it's a tighter spring, stronger bond. It's going to vibrate more quickly, most quickly of all. What if you put on different weights at the end of a spring? If you put on a light weight, it can vibrate very quickly. A heavier weight on a spring is going to vibrate more slowly. So that changes the frequency too. Well, what's our weights here at the end of our springs? They're atoms at the end of chemical bonds. So if this is a hydrogen, it's going to vibrate very quickly. If it's an oxygen atom or an alcohol group, it's going to vibrate a little more slowly. Chlorine, bromine, iodide, those are heavier atoms. They're going to vibrate even slower. And so if we know the frequency, we can actually tie them in or relate them to the bond strength, single bond, double bond, triple bond, and to the atom size, hydrogen, oxygen, chlorine, nitrogen. And those are our functional groups, right? All functional groups are made up of different atoms and different types of bonds, single, double, triple. So that's the idea. Knowing the frequency and having some table that matches up the frequency of the functional group, that identifies the functional groups in our molecules. Awesome. Okay, so here is one correlation table I'm going to give you this one. You can find it on Canvas, and we'll take a look at it a little more closely in a minute. But a couple important details. One, you don't have to memorize it. However, I would advocate memorizing some sections just to speed up the process. I'll point out those most important sections in a minute. But otherwise, you get a copy of this to use during the exam. There's a lot of information here. You can spend a lot of time here. You don't want to waste too much of your exam time going over this. You want to hit the most important, most helpful information first, and that's what I'm hoping to have you memorize, or I'll suggest that you memorize. Definitely get some practice using this table as you do the homework. So either display this on one screen as you work on the homework, or print it out if that's more useful to you. Second idea, these correlation tables are averages, right? So I had some students in the past say, oh, I have a peak at exactly 1710. It must be a carboxylic acid. Well, the ketone's at 1715. That is really close. These are really just average values. So most ketones have peaks around 1715 reciprocal centimeters, but not all ketones are exactly 1750, just on average. And these numbers are so close, you really can't identify which functional group is based on this exact peak position. All we really can say is if you get a peak in the region of 1670 to 1780, it's probably a carbon-oxygen double bond. Or is it? Is there anything else in this region? Yeah, right over here, carbon-carbon double bonds are near in that region. And so is a carbon-nitrogen bond, which unfortunately is not on this list. And that's because they're less common, but it's still possible. So we'll talk about that in a minute. So that's the second bit of warning. Be flexible when you use these correlation tables. For example, if you see a peak at 1650, that's what you see in your data, and you come over here and say, nope, it's not here. Wait. Be a little more flexible. I know the lower end is 1670 to 1780, but these are average values. 1650 might be close enough, and that might count. So be kind of flexible. Cool. All right. There's a whole bunch of information here. You can look at it and analyze it all you want, but here's the main points. Let me double check. I don't think there's anything down here. Nope. Let's go to the main points. All right, these are the most useful regions. These are the ones I really recommend that you memorize. Group second hydrogen bond usually gives a peak around 3400. That's on the far left. We actually saw it over here in ethanol. Where did ethanol go? It's right down here. So as you look at the spectrum, IR spectrum, infrared spectrum, the data for this molecule, the biggest peak is, I hope you see it's clearly, it's upside down. You have to get used to that, but this is the biggest peak. It's the widest, and it's the farthest down. Well, this one might be just as far, and so is this one. But definitely this is the biggest. And it's also the most important one. This big, huge peak is due to the OH group, the oxygen-hydrogen bond. Light around 3,300 or 3,400, right? Average values of the correlation table. That light is being well absorbed by this bond between an oxygen and a hydrogen. So an oxygen and hydrogen is found in an alcohol group, but it's also found, where's my correlation table? It's also found in a carboxylic acid, right? It's over here, correlation table, come back. Somewhere. There we are. Okay, so the alcohol group is more common than carboxylic acid. So yeah, the alcohol group, 3,400, 3,650, but a carboxylic acid also has an OH group. Now, it's right next to a C double bond O, which is kind of like those two heavy atoms. So it changes it a little bit. Not exactly 3,400. Okay, that's helpful, right? So if you see a peak at 3,400, it's probably not the carboxylic acid group because that's at a different wavelength. It's pretty close, 3100, 3400, that's still far enough away. The OH group of an alcohol. It's pretty distinct in the IR. You wouldn't think of it as a carboxylic acid, even though it's an OH group. Correlation table, take a look at it. It'll be helpful to you. Okay, back to the key regions. Hydrogen bonding is not just OH, it's also NH. So that's the amines and the amides. So 3400, it's really an OH group corresponding to alcohols, less often carboxylic acid or phenols. The phen, I think in a homework problem you saw that phenyl with the YL is the nickname, the common name for a benzene ring. So the phen means on that benzene ring, put an alcohol group, the ol group, and if the alcohol group is attached to benzene, it's close to this, 3400. But most of the time, peak at 3400 is screaming, I'm an OH group of an alcohol. It's also screaming, I'm an NH group for an amine or an amide. How do you tell the difference? It's not always clear, but if you had the chemical formula, and in your formula there's no nitrogen, and you have this peak, well then it has to be the alcohol. And if you don't have an oxygen and you have a nitrogen, well then it's got to be an amine or amide. So the chemical formula would be helpful narrowing this down. But there's also some data. Sometimes the NH group, you see a little peak, a little spike in it. And if it's smoother, it's more oftentimes an OH group. We'll go over that in a minute. Right now, if you're making notes, I make a key IR peak set of notes. The first thing is OH and NH at about 3,400 reciprocal centimeters. Second idea is right around 3,000. Check and see if there's any peaks immediately to the left. It's usually due to a carbon-carbon double bonded hydrogen. What does that mean? This bond right here absorbs infrared light just above 3,000. And a sp3 hybridized carbon with the hydrogen, that bond absorbs just below 3,000. So that's important. That'll help you find out if there's a carbon-carbon double bond in your molecule. If you can see a little peak, a little bit greater than 3,000. And it turns out that the alkane functional group, CC, single bonds and alkane with a hydrogen, very, very common. Almost every organic molecule is going to have peaks just under 3,000 because most organic molecules have the alkane functional group somewhere. That's the second key step, key peak, the 3,000 mark. Just above it could be an alkene. It could also be the hydrogen on a benzene ring, right? Because this carbon is also sp2. Let's draw out the benzene ring. There we go. So this carbon has a double bond in it and two more single bonds. That's sp2, hybridized carbon. This bond to the hydrogen should be just above 3,000. Third key peak, go look at 2,200. That's the triple bond region, sp, hybridized carbon triple bonds. And we have two functional groups that have triple bonds, the alkyne and the nitrile. Now, those aren't very common. So most of the time you don't see any peaks around 2,200. But when you do, then suspect either one of these. Now, for the exam or in the homework, you don't have to worry about the next idea. But if you work in the lab and you get really excited around the infrared and you go, come on, let's get some data here. You might be exhaling a lot of carbon dioxide into the room around the infrared spectrometer, and you might start to see a peak grow as more carbon dioxide starts absorbing infrared light. And it absorbs light around 2,200. So keep the infrared spectrometer well ventilated because I have seen this happen. After the end of a day, it's a small room where the instrument lab is kept. Carbon dioxide can fill the room and start to creep up an absorption around 2200, and that's a false positive for a triple bond. And instead, no, you're getting sp hybridized carbon dioxide, right? This carbon's sp hybridized. Okay, just a little aside for the experimental chemists of the future. Fourth tip, and actually this is the last one. Go look at 1700. That's where the double bonds absorb. This one is the strongest, stronger and broader. The peak will be wider for a carbon-oxygen group. That is a nickname carbonyl. So a carbonyl group is found in a ketone. A carbonyl group is found in an aldehyde. A carbonyl group is found in a carboxylic acid. The C double bond O group is called the carbonyl group. And the C double bond O absorbs near 1700. Carbon-carbon double bonds also absorb near 1700. Actually, a little bit less than that, around 1650 or so. Carbon-nitrogen in between that. They're all around 1700. So if you see peak around 1700, if it's kind of wide and very strong, meaning it reaches near the bottom, highly suspect it's a C double bond O. If it doesn't reach the bottom, it's kind of weaker, then it might be CC or CN double bond. Those are the four regions that we most look at. Those are most helpful for analyzing your infrared data. There is a fifth region. It's called the fingerprint region. And this is a region just under 1500. I advise that you don't go into that region. It's on the right side. There's oftentimes a whole bunch of peaks there. A lot of peaks overlap there. It's not too useful unless you have a computer or a big binder full of infrared spectrum. It's called the fingerprint region for a good reason. It turns out that the exact set of waves and peaks out there that you see is very unique to individual organic molecules. So just like a fingerprint, no two people have the same exact fingerprint. Same is true for infrared data below 1500. The peaks that you see there, the shape, the height, the width, they're very unique. The whole spectrum is very unique to a molecule. So if you look at the infrared spectrum and you look for specifically a fingerprint region, you get another molecule that has the same fingerprint region. They're probably the same molecule. And so we have computer databases where a whole bunch of collection of infrared data is in there. And you scan a new unknown molecule and you can ask the computer, hey, go match it up against the library, our database of infrared spectra, and see what you find. And it'll come back, hopefully, with some hits that are like molecules are really close, and it'll tell you how accurate it is and give you some information that might lead you to your unknown compound. So in the lab, the fingerprint region is very useful. Not so much on exams because we don't get a database to go and look up infrared data. Okay, let's get a little more specific. Here we go. Here's the regions. The first region is the NH and OH. That's around 3400. The CH region's right here at 3000. So just above it is the hydrogen attached to sp2 hybridized carbon, a carbon-carbon double bonded carbon with an H. Just below 3000 is an alkane, kind of boring. You almost always see peaks just to the right of 3000. Around 2200 reciprocal centimeters, yep, right here. That's your triple bond region. And your double bond region is centered around 1700, but be ready to go above 1800 or just below 1600, right? Because these are average values, 1700, things on the correlation table. Fingerprint region, yeah, I don't advise going into this region looking for peaks. The correlation table does have a few peaks listed, but I don't trust it so much. And usually there's enough data elsewhere to help me identify my molecule. So I really only look at these four regions. Cool. All right. Do we go over all the overview? Can we actually try analyzing some data now? No. So sort of. Let's look at some data, get a little more feel for each of these four useful regions. Back to the first one, hydrogen bonding. So here's another alcohol It's 4 carbons, 1 butanol is a IUPAC name, but here's the structure right here. And it has the alcohol group. But without even looking at the answer, that is, here's the structure, that's what we're trying to find out. If you just look at the data, you go to around 3,400. I know 3,400 is closer to here, so 3,300, close enough. We get a nice, broad, and smooth peak. It's not jaggedy or sharp here. It's very smooth. That suggests it's an OH and not an NH. And it's very wide, very strong, around 3,400. Yeah, clearly an OH group once you get used to seeing these. Here we have an amine, and over here we have an amide. So we're looking at the NH group. NH there, NH here. And now you get a rounded curve, and it's a little spike here. And that indicates it's probably not OH, but NH instead. Actually, more importantly, is that this peak is only around 60%, whereas OHs are usually the strongest peak. It's around the 0% transmittance. Most of the light is being absorbed. And this is not very strong. So that suggests is NH. The strong one, strong means very low, near the bottom, that suggests OH. Also, this spike is really saying it's probably NH and not an OH. Got 1 spike here, got 2 here. Some students think, oh wait, because there's 1 H and 2 H's. That's not always true. So what's more important is, hey, this is not nice and rounded. There's actually spikes here. There's a spike here, and it's around 3,400. So I'm thinking it's OH or NH, but the spikes are saying NH. And if you know there's an NH group, that means it's an amine or an amide. Those are our 2 most common functional groups with a nitrogen. And if you got an OH around 3,400, well, then we got an alcohol. Cool. That's the first region, 3,400, OH and NH, or alcohols, amines, and amides. Second area at the 3,000 mark. So let's go to 3,000. It's right here. So all the infrared spectra that you'll get on exams and in the homework, you'll find a 3,000 marking. And sometimes you don't get grid lines, so you have to make your own or just estimate it. If you just go up here, you can see that these peaks are above 3,000. That's because this molecule has hydrogens on the C double bond C bond, sp2 hybridized carbon. These carbons are double bonded, they possess hydrogens, and these bonds to those H's are absorbing infrared light at this frequency. There's also peaks to the right. Those are not so helpful. Those are the alkane hydrogens. Do it again. So here's the 3,000 mark, and I get a little peak right on 3,000. Well, it's on 3,000. I can't really trust that as a double bonded carbon. Here's a peak right there that's actually below. That's definitely single bonded carbon with an H. But hey, right here at 3020, that peak, I hope you can see, is clearly greater. That's an alkene CH. And that means the molecule must have a double bond, and the double bonded carbons have an H. And it does. Cool. So right at 3,000, go a little bit higher. If you see a peak, like this is a peak, it's kind of like a shoulder of this main peak. But I hope you see that that clearly is a peak there. Upside down peak. That's indicating a carbon-carbon double bond with a hydrogen. And so we know our functional group is an alkene in the molecule. Nice. Okay, go to 3,000. And there are only peaks to the right. Yeah, because this molecule is hexane. There's no double bonds in it. So that was just to keep us honest. And also kind of show that, hey, there's 3 peaks here. 1, 2, 3, they're upside down. But they're all below 3,000. They're all alkane peaks. Whereas this one, ooh, that's nice and sharp, clearly above 3,000. We got an alkene here. Alkene, yeah. Carbon-carbon double bond, there's H's, 3 of them. We also have the alkane, carbon-carbon single bond over here, not so helpful because that's all this, but they're there. That's the second region. Look at 3000, any peaks immediately above. That'll help identify carbon-carbon double bonds. Oh, if you happen to have a molecule that's tetrasubstituted, it will not have any peaks above 3000. Because remember, this peak is actually the carbon-hydrogen bond. The bond between the carbon and the hydrogen. It's supposed to be this bond, but only if there's a H here. So if you have an alkene that's tetrasubstituted, doesn't have an H, you're not gonna have a bond, you're not gonna have a peak there. So I guess what I'm saying is there are alkenes that don't produce this peak. So if you don't see a peak here, you can't say, no alkene. Well, you might have an alkene that just doesn't have a hydrogen. On the other hand, if you do see a peak, like we see peaks here, then you can be fairly confident there's a carbon-carbon double bond somewhere. But this peak, and all those peaks, just above 3000. They are indicating our molecule has an alkene somewhere. Cool, that's the second region. The third region is the triple bond region at 2200. So they're kind of rare because we only have two functional groups, alkynes, carbon-carbon, and nitriles, carbon-nitrogen. And you really can't tell the difference between the two. Sometimes the triple bond is really strong, goes near the bottom. Sometimes it's weaker. This one's medium. It's about half, it's a little more than halfway down. This is the medium-sized peak. This one is strong because it goes really low. These are weak, but they're still clearly peaks. Doesn't go very far down. All these are sharp. They're not very broad or wide. Let's just get a feel for what the correlation table says over here. Back to correlation table. I think it's over here. So in the correlation table, they have intensities listed. Medium, medium, strong, medium. Any weak? Yeah, there's a couple weak down here. And so what we're saying is, as you look at the peak, on average, not every time, on average, some peaks go way down to the bottom. Others just go halfway or so, and the weak ones just a little bump. They were pretty weak. And then if you see, there's the term broad, then you don't, so a strong peak without any little descriptor usually means a sharp peak, like that sharp, and broad means it's a little bit wider at the bottom. That's broad. The OH group of an alcohol, though, is very broad. It's like, you know, like that. Very wide at the bottom. All right, we're still in region 3, triple bonds. Those are pretty straightforward. 2200 rarely has anything unless there's a triple bond. So here's a peak around 2200, right? There's a 2000, 2500, this is about 2200 or so. And then if you have your instrument, can actually go on that peak and actually identify as 2225 reciprocal centimeters, and that's even better. 2200, whoa, this must be a triple bond. Well, I don't know whether it's a CN or a CC triple bond. Turns out the molecule happened to be this, so it was a nitrile group. Oh, and then on the internet, I did find some example where, what is this? This is 2000, here's 3000. So it looks like this is 22, 24, 26, 28. So 2200 is right here. But in this region, it's getting pretty close, 2300. You're seeing a sharp peak here. Hey, that's noticeable. Well, let's do the carbon dioxide. Carbon dioxide, though, will have this other little shoulder here. And that's not characteristic of a triple bonded group. So that's helpful. If you see this little bump and that in the lab, then you might suspect, ooh, maybe not a triple bond, maybe more likely carbon dioxide. And you can test it in the lab. Kind of ventilate the infrared, hold your breath, see if this peak weakens or gets smaller if you ventilate it and get rid of the carbon dioxide. If it does go away, then yeah, you've identified it as carbon dioxide. If it persists, well, maybe it really is a triple bond. Fourth region is around 1700. And that's the double bond region. So here is an amide functional group. We got the C double bond O with an N attached right here. And you go to 1700, which is actually right here, this marking, so pretty close to it, 1640. It's a strong peak. Look how low it goes. It's as low as these other ones. It's one of the strongest, going near the bottom. It's also kind of wide. It does form a little, let's zoom in on it. It does have a little sharp peak right here. You can see right at the bottom of the peak, it sharpens up, but just above it, from here to there, it's actually kind of wide. It's broad. And that's indicated a CO double bond, probably not a CC double bond. A carbonyl group tends to be broader, a little wider near the bottom. Over here, though, we got carbon-carbon double bonds. Look how sharp this is, very pointed, not broad. It's also very strong. It happens to be the strongest peak here. But the fact that it's, all the way up to here, it's just very narrow. The word is actually sharp that you'll see on the correlation table. That's suggesting CC and not so much the C double bond O. Ooh, 1700 doesn't have anything. This is little bump here. Okay, if you take more organic chemistry, actually it might be in physical chemistry, P-Chem, we'll talk about some quantum mechanics involved here. And it turns out the molecule has to have a changing dipole to absorb infrared light. And if the molecule is symmetrical, as this bond stretches, you don't change its dipole, it doesn't have a dipole. So it doesn't absorb infrared light very well. It's very weak. So I put this on here not because, oh no, get worried about it. I'm just saying, look, there are some misfits. Use the correlation table. Be flexible with it, though. So we're supposed to see a peak at 1700 if there's a double bond. This molecule does have a double bond, and it's actually pretty weak. So be flexible. Don't rule out, oh, no double bond because I don't have a big, strong peak here. No, actually, there's a weak one. You might have a double bond. What else do you have? Go to 3000, and whoa, there is a peak here. So this peak is very clearly saying there's a hydrogen attached to a carbon-carbon double bond. Well, if you have a carbon-carbon double bond, there should be a peak here. Well, no, sometimes you just don't. The symmetry of this molecule makes it unlikely to absorb a strong peak. There is a little peak here. And guess what? This actually is the molecule that produces this data. So be a little flexible as you analyze your data. Look at all the data. It was really helpful to see this peak above 3000. That really helped us identify an alkene, carbon-carbon double bond. What else do we have? We got hexene. Here, the strongest peak is way down here. This is medium. It's also sharp, suggesting CC. It's around 1700. I know, it's 1645. It's close enough, though. That's a double bond peak. Cool. And then we got hexane over here, just for contrast. These are medium peaks. They're very sharp, but they're too far away. It's actually in the fingerprint region, right? 1500 and over, fingerprint region. 1700's over here. And in this region, there's no peak. So probably no carbon-carbon double bond. Let's go check 3000, make sure. Yeah, there's nothing to the left here. So it looks like this molecule does not have an alkene. Oh, and what is it? It's actually hexane. No, there was no alkene in there. Cool, let's zoom out. I think that's the end of the data. What else we got? A sample problem. All right, let's work this out. So this is something you might see on your next exam. I'm giving you two pieces of information. Both pieces of information came from the same molecule. The data looks different. The question might simply say, propose a structure. Now, you're not going to know exactly what it is. We need more information and narrow it down to one molecule. We'll see that in the next couple of videos. but we actually can narrow down the possibilities quite a bit. So propose the structure for the compound that produced these spectra. Well, what the heck is this? Well, you got a couple of clues. I would go to the x-axis first. 1,000, 2,000, 3,000. Hey, the numbers are increasing from the right to the left. That's backwards. And these peaks, oh yeah, these are the upside down peaks. This is infrared. So it's up to you to figure out what data you're looking at. This is infrared. This data, the 0 starts over here and goes up to 100. Okay, that's normal. And it's a bar graph. It's not these broad or sharp peaks. It's individual lines. And they're in clusters. Wait, there's a cluster here, cluster there, cluster. This is mass spec, the mass spectral data. Now that you have identified it, and hopefully you've seen the video on mass spectra, now you can analyze it. I like analyzing the infrared first. If I had a chemical formula, I'd probably analyze that first, go after the degrees of unsaturation. I don't have a chemical formula, so, and then some people like, no, I'm gonna go after mass spec first. Your choice, it all works. Just analyze both of them at some point. Infrared's fast, so I like doing it first. First, I go and see, well, around 3,400, this is 2,000 and 1,000. It looks like every peak is 100. So this is 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Yeah, 4,000's over here. And that's typically the range. And around 3,400, ooh, I got a nice smooth peak. Yes, there's a peak at 3,400. Smooth, no spike. It's very strong, comes down low. Those two features, smooth and broad, very strong peak. That's probably an alcohol. Maybe NH. I'll put in parentheses because it's still a possibility, but I'm leaning towards OH because no spike and it's very strong. Second region, go to 3,000, go up, and I do not see any peaks immediately to the left. So I'm saying no, I probably don't have a carbon-carbon double bond, so certainly not one that has a hydrogen. There are peaks over here. Those are alkanes. Kind of boring because most molecules have alkanes somewhere. Third region, 2,200, that's right here. That's going to help identify the triple bonds. And nope, none of those. All right, that's really narrowing down our possible list. 1,700 looks like it's around here, and I got nothing. So there's no double bonds of any type. Wow, okay, so that's narrowing down the possibility. We will want to draw something eventually, and when we do, make sure it doesn't have any double bonds in it and no triple bonds in it, because the data doesn't support it. Data says probably not those things. Oh, and make sure you put an alcohol group in there because the data supports that. Cool. Now what? Switch over to the mass spec. To analyze the mass spec, take a look at the video, and what you'll learn is data comes in clusters. Go to the rightmost cluster. Oh boy. And then, okay, I had another learning opportunity when I chose this data. So I'm not going to do this to you on the exam, but if you're in the lab and you analyze your own, we do have a mass spec and we do have an IR spectrometer. So you might get some real data that might really do this to you. Let's zoom in, please. That's the IR. Here's the mass spec. And let's look at the baseline and look at these tiny little peaks here. There's a peak right there. So the rightmost cluster is right here. Or is it? Okay, so this is real data. That's a surprising look. This is real. Oh no. So again, I won't do this on the exam. I'll make your parent peaks more obvious than that. But the reality is, if you're doing experimental research, you might actually get data that looks like this. So what does this mean? So remember, all these peaks are counting ions that made it to the detector. The biggest ones are the molecular ions. Peaks of greater than the actual molecule are isotopes. Peaks smaller than the largest, the original molecule, are fragments, right? The molecule fell apart. Okay, so go to the right cluster peaks. There's 2 of them here, and choose the biggest one, farthest to the right. Well, they look like they're the same height. So I guess I gotta pick this one. That's farthest to the right. That's the parent peak, the M cation radical. That's supposed to be an M. Why didn't I pick this one? Well, if I pick this one to be the parent, the original molecule, then the peak bigger or heavier than that must be an isotope. And isotopes are rare. That means you don't count as many ions. That means this peak needs to be smaller, a lot smaller than this one. And they look to be the same height. So I don't like calling this one the parent. No. Call this one the parent. Then what is this peak then? Well, it lost 1 mass unit. We'll see why I think it's 1. It lost 1 hydrogen. And that's very reasonable, especially if the molecule has an alcohol group. That's what the infrared data said. We had some molecule, that's supposed to be carbons, there's an OH group somewhere, and this thing had an electron knocked out of it for the mass spec, so now it's a radical cation. Well, maybe the hydrogen left as the radical and left the oxygen with a positive charge. Maybe that's how it fragmented. Maybe it lost its hydrogen. And that would produce this peak, a fragmentation peak. The original molecule, missing an H. All right, can I undo all that messy? There we go. Okay, so here's our parent peak right here. We found it. The next thing they do in the mass spec analysis is get a value for the weight of this. So go down the baseline and read off the number, and it's not here. So what do we do? Well, what are these numbers? Here's 60, here's 80. So in between is 70. This little tick mark is 70. This one must be 75. And that's 80, and this is 85, and this one's 90. Cool. Find another region where there's a lot of peaks. Well, this is 60. We said that's 70. So this is 65. This peak right here is 55. And now I have peaks between 55 and 60. This one is 56. This one is 57. This one is 58. This is 59, 60. I know there's no peak there. But what I'm looking at is this distance is 1 mass unit. This distance is 1 mass unit. I just verified it from counting from 55 to 60, look at all those peaks. So now we have a feel for how wide 1 mass unit is, and we want that one right there. So how far away is it from 90? 1 mass unit? No, it looks like it's 2 mass units away. What about between this one and that one? Well, this distance between these 2 little bumps is a mass unit. I think there's 1 more mass unit there before you get to 85. I think there's a mass unit there. Hey, now I have tick marks here, kind of, right? So this is 85, 86, 87, 88. I think it's 88. This would be 89, that's 90. I think that's at 88. Okay, so we have a mass of 88. Let's zoom out and start figuring out what this molecule looks like. Well, we know it doesn't have any double bonds or triple bonds, has an alcohol, and has a weight of 88. What are we gonna do with that 88? Divided by 12, because it has to have carbon. This is organic chemistry, the study of carbon. So let's see, is it 7 times 12? Yeah, 7 times 2 is 14, carry 1. Yes, that's 84. Subtract that and get a 4. So the number left over is the number of hydrogens. The number you divide by 12, 7, that's the number of carbons. Cool, so there's the chemical formula. That good? No, because the molecule has to have an alcohol. I need an oxygen. So how much does oxygen weigh? Well, go look at the periodic table. The atomic mass is 15.9994. That's really close to 16. So the most common isotope of oxygen is oxygen 16. It weighs 16 mass units. The whole molecule weighs 88 grams per mole. I need to squeeze in an oxygen atom that weighs 16. But 7 carbons and 4 hydrogen already weighs 88. So what I have to do is make room for 16 more mass units. I want to add in an oxygen so I can make this alcohol group. I'm going to subtract out a carbon that weighs 12 mass units, right? We weighed it out 12. And I also subtract 4 hydrogens that each weigh 1. So altogether, this is 16 mass units. If I want to add in an oxygen with 16 mass units. Where's my little scroll bar? There we go. Okay, so I don't like this chemical formula because there's no oxygen. So let's get one. Take away 1 carbon. So now there's only 6 carbons. Take away 4 hydrogens. Wait, there's no hydrogens now. If I get my oxygen in there, yeah, this isn't a good formula either because an alcohol group must have a hydrogen. So what do you do next? Well, let's get some hydrogens. I have to remove an atom to make room for some hydrogen. So let's remove a carbon, weighs 12 mass units. That will allow me to add in 12 hydrogens, each weighing 1 mass unit. So now a good chemical formula is C5H12O. And I did a lot of number manipulation. So let's make sure this still weighs 88 mass units, right? That's how much the molecule is supposed to weigh. The parent peak says 88. Does this weigh 88? Well, there's 5 carbons. There's 12 hydrogens, each weighing 1, and there's 1 oxygen that weighs 16. So 5 times 12 is 60. 12 times 1 is 12. 1 times 16, 16. And yes, you have to do this by hand. Showing your work helps. You do not get a calculator. We're in college. We can multiply and add and subtract. 8. And then 6 and 2 is 8. Yay! This adds up to 88. Good. So this is actually a good chemical formula. It's got an alcohol group that takes care of the O and 1 of these H's. So what are you going to do with the other 5 carbons and 11 hydrogens? Well, make sure you don't put any double bonds in there or triple bonds. And then the sky's the limit. Do you want a straight chain of 5? And then put an alcohol group in there? That works. That's C5H12, or is it? You know what I forgot to do is count degrees of unsaturation. Sorry. Maybe, well, we can't have a double bond in there, so maybe we have rings, right? That's a degree of unsaturation. Let's find out if we can have a ring in our molecule. Count up the degrees. Well, if there's 5 carbons, the maximum number of hydrogens will be 2 times 5 plus 2 more. Let's subtract how many we actually have. We have 12 hydrogens. Make an adjustment for other elements. Well, oxygen, you don't do anything. It looks like the number 0. So don't add any or subtract anything for the oxygen. Divide the whole thing by 2. 5 times 2 is 10, plus 2 more is 12. Minus 12, divided by 2. Yeah, that's 0 on top. It's 0. Yeah, this thing is saturated. I'm not surprised because I worked this out before I started the video. I'm glad I remember to show you. It's a good idea to count the degrees in saturation. And now we know it's saturated. That confirms, that's consistent with our data, the IR data that said, yeah, you didn't have any double or triple bonds in here. We don't have peaks for them. But technically, we could have had a ring. And now the degrees tell us, and that's not consistent with the ring either. So you either have a straight chain. Why did you put the alcohol group on this carbon? Could have been off the middle. It could have been off the end. Yeah, it could be any of those. Why is it straight chain? Why don't you have a branch one? And then put the alcohol here, or put it here, or somewhere else. Or maybe you have this molecule. That's C5H12. Well, then the alcohol group, let's go there. There's lots of possibilities. But we can't have any rings because it's saturated, and a ring is a degree of unsaturation. Here's some possible structures. The question said just propose a structure. I got 5 of them. They may or may not be the answer. We need more data. And that'll be in the next video. All right, until then, see you later.